Okay, so now we've talked about the basics of simple harmonic motion. You got the equations for the period, finding out how long it takes for it to make one full cycle, right? Circle, or up and down, back and forth, whatever it may be. All right, so the other thing we want to do is then also be able to figure out where a point of this thing is, maybe the end point of it, where the mass is at, where the hanging mass is located. Excuse me. And for that, we need to figure out a couple of things, right? We always need to know our position, our velocity, and our acceleration of physics. Those are kind of the basics. So how do we determine those? Well, if you remember, A was our amplitude, okay? So we need our amplitude for this one to actually figure out where it is, interestingly enough, okay? Which I guess is not all that surprising, is it? I mean, we need to know exactly, basically, how far it can go. We need to know where the lowest point is and the highest point are, right? So we can figure out how high it could possibly go. Then we need something with cosine or sine. We need that cycle. Remember that kind of that sinusoidal graph we had? We need to have that to figure out where in our repetition or our periodicity we are. So for that, if this is our graph, okay, amplitude, there's 0 over time, we need to figure out where exactly in that cycle we are, right? So with time here, you're going to change how high up you are, and that's going to be your x position. So I guess it's not that surprising either. We need some kind of a sinusoidal or cosinusoidal function. All right, so, and then omega, that was our angular frequency. So how long does it take to actually go through one full cycle? Okay, T for time, again, everything's dependent on time in physics, and phi. Okay, this is a new one, phi, all right? It's another Greek letter. And what is that? That is just basically where do you start in the cycle. So when you start timing it, I pull it down here, and that's really where it starts. Do I wait until it gets all the way back down there again? Or maybe when I take and time this thing, or when I figure out its position, I'm actually looking at it starting the clock when it crosses the board here. Okay, so then that is a very different thing. So I will have a phase shift. Okay, even though I may start here, physically, where I actually start looking at the thing, I don't actually start the clock until somewhere in there. So maybe I start the clock when it's at 0 instead of below or above that point. So that lets you kind of offset things. But you can see the amount of time it's going to take is not going to be dependent on that at all. The only thing that's going to happen with that is it'll change where you're at for your x point. Okay? What about velocity? Well, velocity is dependent on position, isn't it? Position over time. Okay, so if you look at this, how do I get here? I popped out a negative. It's changed to sine. I've got another angular frequency popped out there. The real answer is calculus. If you want to know how to do this right here is the derivative of that one. And this is the derivative of that one. If you're not taking a calculus-based class, you don't have to worry about it, okay? So we just get to here, magically. So what does the velocity have to do with? How high up or down you can go, right? How far you can stretch this thing, your amplitude, how quickly it goes through that, some kind of a sinusoidal function because you're going through here, right? Instead of this, if you increase your angular frequency, you may actually look something like this, amplitude over time. If you increase your omega, right, you're going to have something with a lot more wiggles to it because it's going to go through that cycle much more quickly. So increase your angular frequency, and you get a much faster wiggle. Slow down your angular frequency, and you get to a smaller wiggle. And where is it at? How fast is it going? Well, again, your velocity is not constant on this thing. Look at this. As I stretch it down here, it's going to be going blazing fast to shoot up, and then it slows down when it gets to here, kind of carries up, and it stops up here, and then it starts to accelerate back downwards. So your velocity is constantly changing. And it's going from a positive to a negative to a positive to a negative. So it makes sense that we have to include a negative in here to account for that change in direction. Okay? We still need your sinusoidal curve, like we have here. Do we bunch it up or do we spread it out? Right? Bigger number here means you get more curves per unit time. And again, it's all still dependent on how your frequency is working, right? Your angular frequency, how much time goes by, and again, where you start, right? When I start the clock, am I down here so I have a positive velocity, or am I up here when I start my clock and so I have a negative velocity? Again, it matters, and your sign changes. What about acceleration? Acceleration also changes. Remember Hooke's law. The more you stretch out a spring, the more force you have. Now, the mass isn't changing. So force is mass times acceleration, okay? So if the mass of this thing isn't changing, that means the acceleration has to be changing the more I stretch it out. So I get a higher acceleration for that spring, and look at that. You can see how quickly it just snaps up, right? Boom, right up to the top. If I stretch it out a little bit, a lot less acceleration. So your amplitude definitely has something to do with how fast you're accelerating, how fast you're going, and what your position is, okay? Weirdly, it doesn't have anything to do with how long it takes to go through one full cycle. That's still independent, which is kind of interesting, okay? Your cycle is only dependent on this one. It's only dependent on your angular frequency. All right, but your acceleration, again, it has to change direction because you're accelerating upwards, so that's positive acceleration, but once it gets to the top, it has to be able to accelerate back downwards, so it can flip, okay? Has everything to do with your angular frequency, how long it takes to go through one full cycle, okay? And that's going to modify how many wiggles you get in your cosine or sine function, okay? And then inside of that, again, angular frequency and time, and then where you start your snapshot, okay? So maybe you have to pull it down to get it started. Maybe you have to bunch it up to let it go, right? But I can let it go from the top because I don't have to pull it down, right? Gravity will actually do that for me. If I have it above its relaxed length and let it go, it'll still bounce around, okay? So this is just shifting where you're starting. Am I looking here and starting there, or am I starting up here, right? That's my phase shift, my feet, all right? And that's it. So if I want to know exactly where a hanging mass off the end of this thing is, where the end point of this spring is, for instance, right? I have to take and figure out how much amplitude I'm giving it, how long I stretch it. I have to know the frequency it has, which again, remember, it only has to do with the K value of this thing and the mass that's attached to it. That took me a second, right? Okay, so for a spring, the only thing that has to do with is, again, the mass attached to it and the K value for the spring, how stretchy or stiff it is, okay? So that's basically it. You want to know your position, amplitude, plug in cosine. All of this, instead of the theta we used before, this is in place of the theta. So this will change, right? It will change as you go further and further in time. You've got to figure that out before you can figure out the function cosine on your calculator and plug in the value you find there, okay? Starting place in your cycle, how much time went by, angular frequency, amplitude, and then cosine unit of that function, okay? So basically the same thing down here, except for it switches to sine, and you get a negative. Don't forget these equations. You're going to need them for your homework.